In this video, we will be looking at a couple different theorems that will help us find techniques we can use to find the zeros of polynomials. In the last video, we were looking at factoring things completely, and we had to guess for some of what the initial zeros were used to use synthetic division to break the polynomial down, and so these theorems are going to give us an idea of where to start. One of the most important theorems in math is the fundamental theorem of algebra, and it sounds really important, but it's saying something that we've been talking about for a number of weeks now, which is that when we have a polynomial of degree 1 or higher, that it's going to have at least one zero that is complex. And so that means it doesn't have to be a real number, it could also be an imaginary number. And when you think about zeros, for us, we're trying to find the ones that are real numbers because those will lead us to x-intercepts of the graph. So in general, if I have something that is to the first power, I'm going to have at most 1 0. But then if I took that and expanded it to end up with something, say, squared, I would have 2 zeros. And if I have something like this, this is telling me that I will have at most 3 zeros. They might be multiplicities, so it's repeated. In that case, I wouldn't have 3, but I would have at most 3. And that they aren't necessarily all going to be real numbers, they might be complex numbers, imaginary numbers. This second theorem lets us know that if we do end up with imaginary numbers, that they will show up in conjugate pairs. So if I had something like 3 plus 2i, 3 minus 2i is also going to end up being one of the zeros. If I have negative 7 minus 5i, I will also have negative 7 plus 5i. So if I have imaginary numbers, they show up in conjugate pairs. And the conjugate part of it is that the sign of the second term switches from positive to negative. The real part, in this case the 3 and the negative 7, that part of the sign doesn't change. Similarly, for irrational zeros, these are the ones with square roots, ones that come from the quadratic formula. They also show up in conjugate pairs. So I might have something like 6 plus the square root of 2 and 6 minus the square root of 2. If I think about some of the ways that I see the quadratic formula, I might have negative 1 plus the square root of 7 over 4 and negative 1 minus the square root of 7 over 4. Again, that change of sign is happening before, in this case, the radical symbol or the square root. Now, this is one of the most important theorems that we'll use for trying to completely factor and graph polynomials of higher degree. This tells us that by looking at the first and the last term of a polynomial, specifically the leading coefficient and the constant term, that will give us an idea of any rational zeros that may exist. Rational meaning something that shows up like a fraction. So that could be a whole number like 3. It would show up as 3 over 1. In this theorem, we have this phrase that you may not have seen before called relatively prime. That just means that the two numbers are prime in relation to one another. They don't have any common factors. So examples of relatively prime. Remember that a prime number is one that's only divisible by 1 and itself, like 5 or 7, but these numbers don't have to be prime numbers themselves. I could have something like 25 and 49 are relatively prime. They don't have any factors in common. 25 is 5 times 5, and 49 is 7 times 7. I could have something like 7 and 18. 7 has only one factor, which is 7, and 18 is made of 2s and 3, right? 3 times 3 times 2. So they don't have any factors in common. So we're basically just a fancy way of saying I have a fraction that can't be further simplified. Now, if there is a zero that is a rational number, it's going to be of the form taking any of the factors that are in the last term and dividing by the factors in the first term. We'll do some examples to show you what that looks like, how to find them. So here's a first example. We have a polynomial that's raised to the fourth power, and we want to find all the possible rational zeros and then use that information to find all the zeros. We know from the fundamental theorem of algebra that there is going to be at most 4 zeros in this because it's raised to the fourth power. And the possibilities for the rational zeros are taking that last number, which is a -4. All the factors of -4 are plus or minus 1, plus or minus 2, and plus or minus 4. These are all the numbers that can divide evenly into that. And so we've written those in the numerator of this fraction. Then looking at the leading coefficient, the 3, we want to look at what are the possible factors of that. Well, that's plus or minus 1, plus or minus 3. Those are the only numbers that could possibly divide evenly into 3. And then we take all of the combinations and write out the possible zeros. So the first one, 1 divided by 1 gives us 1. And then 1 divided by -1 gives us -1. 2 over 1 and 2 over -1 gives us these. And then 4 over 1 and -1 gives us these, right? So we're going to take all the different possibilities. These fractional ones are coming from, like here we've got 1/3, and then we've got 2/3, and then we've got 4/3. And again, all of the positive possibilities and then also negative possibilities. Now that's a lot of possibilities that we can have. We learned in the last section that we can plug these in to the original to determine whether any of them actually work. So let me copy this down. So now we sort of have a starting point. So our original is 3x to the fourth minus 11x cubed plus 10x minus 4. As I mentioned last time, we always want to try to start with 1 and -1 because they're the easiest to plug in. So let's try x equals 1. I'm going to plug 1 in for x everywhere. So that'll be 3 times 1 to the fourth power minus 11 times 1 cubed plus 10 times 1 minus 4. Plug that into a calculator. That's -2. So this is not equal to 0. So 1 is not a 0. Let's try -1. So I'll have 3 times -1 to the fourth. So let's see, I'm going to have 3. It's going to change to plus 11 minus 10 minus 4. Yeah, that actually really ends up being 0. So we know that -1 is one of our zeros. So we'll use that to take the existing polynomial that's raised to the fourth power and break it down to something to the third power, and then we'll repeat. So I'll use synthetic division to divide. I take the coefficients of the original polynomial. Notice that there's a squared term missing, so I have to add a 0 as a placeholder. And then we bring the first number down, and then we multiply, right? -1 times 3 is -3. Add down. This will be a 14, -14, -4, 4. This is 0. So synthetic division ends up giving us a 0 here as a remainder, and that happens when you end up with something that is a 0. And again, when you plug it into the function, you also get 0 as the output. Makes sense, right? Because what we're saying is that -1, 0 is one of the points on the graph. The output, or the y value, is equal to 0, and so it's crossing the x-axis there. Okay, so our new polynomial that we have is 3x cubed. We're going to drop down the degree by 1, minus 14x squared plus 14x minus 4. And now we're going to repeat the process. We know from the previous work that we were doing that x equals 1 doesn't work, so we won't try that. We could try -1 again. It might be that -1, it has a multiplicity and it is showing up as a root twice. So let's do that. Let's try x equals -1 again. So I'll plug that into my new polynomial. So I get, this will be a -3, that'll change to plus, minus 14, minus 14, minus 4. This is definitely not equal to 0, right? All right, so I'll just give you a little bit of a hint. It turns out that x equals 2/3 is going to be a 0. Let's plug it in just to make sure. 3 times 2/3 cubed. And we can just use our calculator to quickly do this calculation. Oops. And you should get 8/9 minus 56/9 plus 28/3 minus 4, and this will end up equaling 0. So since we found another 0, we'll repeat synthetic division again. We're going to put 2/3 here, and then the coefficients were 3, -14, +14, and -4. So again, what we're doing is we're taking those original possible zeros and we're trying to break this original polynomial down to find hopefully 4 zeros so that we can put it in its factored form with 4 linear factors together. All right, so we bring down the first number, and then we multiply 2/3 times 3 will give me 2. Add 2/3 times -12 is -8. Add to get 6. 4 here and 0, as we suspected. So my new polynomial is now 3x squared minus 12x plus 6. I'll take a common factor of 3 out of each of these terms. And it looks like this is one that I cannot factor. So now I'm at the point where I need to do, oops, that should be squared. Now I'm at the point where I need to do the quadratic formula, right? Okay, so A is 1, B is -4, and C is 2. Negative B, so that'll change to a +4. B squared will be 16 minus 4 times 1 times 2. Okay, so this is 4 plus or minus the square root of 8 over 2. So minus, that's 2 square root 2. And when you simplify here, make sure that the 2 divides into the 4 and then also into the square root. So I'm getting 2 plus or minus the square root of 2. So here's that example where the irrational roots or zeros show up in a conjugate pair. So just to recap, the zeros that we found were, let's go back up. Originally, we found -1 and 2/3. X equals -1, 2/3, and then we just found 2 plus the square root of 2 and 2 minus the square root of 2. Now the complete factored version of the original is so we had 3x to the 4th minus 11x cubed plus 10x minus 4, and this equals x plus 1. Remember, we subtract the 0. We have x minus 2/3, and then we have x minus 2 minus the square root of 2. I'm changing the sign because here I'm subtracting both of these terms here. And then for the next one, I'll have x minus 2 plus the square root of 2. Again, I'm subtracting both of these terms here. Now, before we are done, I just want to point out, let's look at this and think about if we took all of the x terms and we multiplied them together. We would end up getting x to the 4th, but here we have a 3 as a coefficient. And the question is, where does that come from? Well, when we have a fractional root, like we do right here, what we do is we don't leave it as a fraction, we multiply through both of those by 3. So if I do that, I'll end up with that particular term being 3x minus 2. So this is what we should actually have. And that gets us the idea that when we multiply everything through, we'll get that 3 as our leading coefficient. We only do that for rational zeros that are in fraction form like that. So there's our final answer. And again, our main purpose is to find the zeros that we can use for graphing, and those would have ended up being just the -1 and the 2/3. All right, let's look at another example like that. Here's another example, different polynomial. Let's start by listing out what the possible rational zeros are. They're going to be factors of the last number, which is -2, over factors of the first number, which is +2. So that is plus or minus 1 and plus or minus 2, and then plus or minus 1, plus or minus 2. These are all the numbers that can divide evenly into those two. So putting these together, I have plus or minus 1, plus or minus 2, and plus or minus 1/2. So then I'm going to try to test some of these. Let's try, because it's always easier, let's try x equals 1. And when we plug that into the original, we get 2 times 1 plus, that'll just be 1 plus 2 minus 3 minus 2. Again, I'm just taking 1 and I'm plugging it into this original up here. And that's going to end up being 0. So we know that 1 is one of the zeros. So we switch to synthetic division so that we will have, we'll be able to get a polynomial that is to the 3rd power. So I'll put 1 here and then take the coefficients. 2, 1, 2, -3, -2. They end up being the same numbers as when you plug 1 into the original. Bring the first number down and then multiply, add, multiply, add. Okay, so my new polynomial is 2x cubed plus 3x squared plus 5x plus 2. All right, then I'm going to repeat again. I want to go back and look at my possible zeros and see if I can find another one. I'll make it easy on you and tell you that another zero is going to be negative 1/2. So we plug that in to our new equation. To see if that equals 0. This ends up being 2 times negative 1/8 plus 3 times a 4th plus, no, that'll be minus 5/2 plus 2. And if you plug that into the calculator, you'll get that this is equal to 0. So then we'll use synthetic division on the equation that was to the third power. Again, we just grab the coefficients, bring the first 2 down, and then multiply. 2 times negative 1/2 is negative 1. Negative 1 will be 4, and we get 0. So this is 2x squared plus 2x plus 4, or factoring the 2 out, x squared plus x plus 2. I don't think that we can factor that, so we have to go to the quadratic formula again. So A is equal to 1, B is equal to 1, and C is equal to 2. So we'll have negative B, negative 1, B squared 1 minus 4 times A times C. Negative 1 plus or minus, oh, that's going to be an imaginary number. It looks like it's a negative 7 under the radical sign. So we get negative 1 plus or minus the square root of 7 times I over 2. So we have 4 zeros that we found. The zeros are x equals, what was our first 0? I think it was it 1? It was 1 and then negative 1/2, 1 and negative 1/2. Then we have negative 1 plus square root of 7 times I. That I is not underneath the radical symbol. So there are our 4 zeros. And then the factored form here is going to look a little strange. It's going to be x minus 1, x plus 1/2, and then we'll have, I'm going to do this with brackets here just because this is going to be complex looking. I'm going to take x minus this number, negative 1 plus 7, square root 7. That's one whole factor, and then another one is x minus this whole number, right? We'll talk about this in class on Wednesday. A lot of times there are other books that will write this as an irreducible quadratic. So instead of writing it that way, they would have just left it in this format here. So some places do that. And again, that 2 that we factored out from above is going to end up showing up here, and it should be 2x plus 1, and then an x minus 1. And then the rest of that business. I'm going to write it the way that it was up here, which was an x squared plus x plus 2. So this is our factored version, right? Yeah. All right. So those examples are lengthy, but that's the process that we use to find zeros for graphing when we're doing it by hand. There's one more theorem in the text. I'll just leave it up here for you to look at. You can look at it in the textbook if you want. We don't use this too often anymore. There are other techniques we can use, like graphing calculators, to find this. But it was a way of narrowing down which zeros we were going to plug in by looking at the changes in the sign between terms. When we plugged x in versus negative x, if the terms changed from positive to negative, that would help us determine how many of a particular type of zero there was. We're not going to use this very much in this class, but I just wanted you to know that it exists. All right, have a great day, and thanks for watching.